Welcome back. We are talking about how Einstein's theory of general relativity is different than Newton's law of gravity, and how it affects the surfaces around very massive objects like black holes. So we have talked about Newton's laws. We talked about how Einstein's is different and how light, in fact, even though it has zero mass, must be affected by gravity in the same way that other things are. And so what is this curved space-time thing that we're talking about? First of all, what is space-time? We're not really going to be getting into the details of how space and time are connected, but in this theory, time really is a fourth axis of the spatial dimension in some very real ways. But really, when I talk about curved space-time, I'm really, for your purposes, can think about this just being curved space. So what is curved space, and how does that affect objects' motion through space? So again, this is all very difficult to picture in a three-dimensional sense. So we're not even really going to try. Let's imagine a two-dimensional universe, right? So our universe has three dimensions. You can move left and right. You can move up and forwards and backwards, and you can move up and down. Right? A two-dimensional surface only has two of those directions. Let's say left, right, and forwards, backwards. There is no up, down on this two-dimensional sheet. Our three-dimensional brains can imagine curvature in two dimensions. Our three-dimensional brains can't really picture three-dimensional curvature. So let's try to picture curvature on this third dimension and see what that happens. So if our rubber sheet is perfectly smooth and uncurved, this virtual two-dimensional ant will travel in a straight line, and that actual line will be perfectly straight. Now, if we were to put some sort of weight on this rubber sheet, that weight will, as you know, deflect that sheet. It will cause it to curve. And so this ant, even if it tried to make a perfectly straight path on this sheet, may have to, in fact, a perfectly straight path for this ant through this curved space will look like a curved path to us. And it might even have different distances than you might think. The same equivalent thing is happening to us in three dimensions from around massive objects. This also explains why light is deflected. Light is simply trying to make the straightest path it can between 2 points, but a straight path on a curved space looks like a curved line. This is the shortest path this is the shortest distance between these 2 points, actually, and not what you might think as a straight line. And so light itself will also be bent around massive objects because it's the space around the massive object that's bent, and the light interacts with that space in the same way that everything else does. Okay, here's maybe a better example, and the analogy I like to make here is, if you've ever been to a science museum, raise your hand. Excellent. I'm glad most of you have been to science museums. Okay, now raise your hand if you've ever seen one of those contraptions at science museums where you drop a quarter in the top and it looks like a giant kind of inverted funnel, right? You drop a quarter in the top, it's got a little ramp, and that quarter actually makes orbits around the center, and that orbit gets smaller and smaller and smaller, and the thing goes faster and faster and faster until it finally drops down, and you've deposited your donation to the science museum. Raise your hand if you've played with one of those things. Not as many of you, but you can hopefully have seen them happen at some level and can appreciate it. That is actually how gravity works. The curved plastic that you see in that thing represents the curvature of space-time. And you launching your quarter on that ramp gives it a certain velocity that lets it orbit the center in the same way that the Earth orbits the sun. And if there were no friction, if it were a frictionless surface, that quarter would continue to orbit and not go down at all. The fact that there's frictional forces robs energy from the system, and eventually it spirals in and eventually falls down to the bottom. But with no friction, it would be happy to do there, to do to orbit there forever. Now, so the next time you're at one of these science museums, try this experiment. Instead of starting the coin at the very top of the ramp, start it halfway down the ramp. By the ramp, I mean there's usually, in addition to the funnel, there's a little ramp that gets the coin up to the right speed so that it enters a circular orbit. If you start it halfway down that ramp, it's going to be a lower speed. And so it's not going to enter circular orbit. It's going to enter an orbit where it takes it all the way down sort of to the middle and then back up again, and down to the middle and back up again. It's going to enter an elliptical orbit. It's going to be all, Kepler's laws are happening as you watch this thing. You can see that it'll enter an elliptical orbit. The sun will be at one focus of that orbit. And it will be moving a lot faster when it's down here than it will be when it's back up here. Go ahead and give that a try the next time. And you can see how circular orbits happen. You can see elliptical orbits happen. You could even, if you give it too much energy, it will come down and it will fly out, and you can have an unbound orbit. You can simulate all kinds of cool gravitational stuff with those science museum toys. But all of this gravity can be explained in a very similar way. Space is actually curved in that particular way, and the Earth is like a giant coin that has a frictionless orbit around the sun and stays in perfectly stable orbit. Okay, now there's some other differences between Einstein's theory of space of gravity and Newton's theory of gravity, and this is where the time part of the space-time comes in. Time itself behaves differently depending how space is curved where you are. And this is the other difference between the two theories. So, for instance, if you have two clocks and they are synchronized far from other masses, and you bring one close to a very massive object, meaning space curves for it more, those time in that particular object will move slower than it does for an object that is not near that massive object, or is near a less massive object. This is actually one of the major plot devices in the movie Interstellar. If you'd like to go see that movie, I recommend it. The science is very good in that movie until the very end. But they take, one of the plot elements is this effect is magnified the closer you get to a black hole. And this can actually be rather an important time difference. It's very small on the surface of the Earth, extraordinarily small, but measurable. We have taken a clock, two clocks, just this experiment, kept one of them on the Earth, put one of them in a satellite above the Earth, not even all that far up, where the space is curved just a little bit less, and lo and behold, a measurable difference in the time rate between those two gets set up. Time is actually running slower on the surface of the Earth than it is in low Earth orbit. Now, we're talking about, I don't even know what the numbers are, but probably nanoseconds per century. It's not a noticeable effect. It's measurable, but it's not noticeable in any particular way. Now, black holes, though, space gets curved a lot more, and you can talk about much, much bigger differences in the rate time runs between those places and places that are far away. In fact, if you've ever used GPS, and I'm guessing almost all of you have used GPS, those satellites will not work unless you account for this effect. Timing is very important. In fact, they do all their locations based on timing, and milliseconds and nanoseconds become very important. And if the time on these orbiting satellites were not corrected for this effect, it would not work at all. So not only is this a measurable effect, but you have to account for it when you're making GPS calculations. So that's exciting. Okay, now we have another important concept to get through here to understand if we want to understand black holes, and that is the concept of escape velocity. So let's very quickly talk about escape velocity. We talked about escape velocity a little bit when we were talking about gravity at the beginning of the semester. We specifically talked about orbital velocity, and we specifically talked about there is a velocity beyond which you will actually escape from that object. So let's define what we're talking about a little bit more here. escape velocity is the velocity necessary to escape an object's gravitational pull. What does that mean? Well, you can't ever really escape an object's gravitational pull. It extends to infinity. But what we mean is, without giving it any other forces, obviously, the further away it gets, the weaker that gravitational force will get. If it's not moving fast enough, eventually, the recessional velocity will decrease to 0, and it will start to fall back again. If it's greater than a certain amount, it will continue to travel away from the object forever. And it will, at distance equals infinity, have some non-zero speed, positive speed. The escape velocity is the hairline velocity between those objects which will be brought back eventually and those objects which will not. In other words, it will continue to slow down, but it will reach velocity equals 0 at a distance of infinity. And this is the equation that lets you figure out what that velocity is. I've got it here. Let's go ahead and use our whiteboard to write it out. So here we go. Escape velocity, I'll do it v sub e. The escape velocity squared is 2 times g times n divided by r. So let's define all of these terms first. VE is the escape velocity. What kind of units would you expect for a quantity called escape velocity? Well, it's a velocity. This could be meters per second. This could be kilometers per second. It can be whatever distance divided by time unit you want, really. G we've seen before. This is the same G that shows up in Newton's version of the gravitation force equation. This is the universal gravitational constant. If you don't remember, it's just a number with units, 6.67 times 10 to the negative 11. And it's got weird units, meters cubed per kilogram times second squared. Great. What is this M? This M is the mass of the object you are trying to escape from. There are two masses in the force of gravity equation. There's only one mass here. The mass of the object that's actually trying to do the escape is not important, as long as it's much, much less than the object you're trying to escape from. And in all of our cases, it will be. So the only mass that matters anymore is the mass of the object you're trying to escape from. The Earth, if you're talking about the Earth. The Sun, if you're talking about the Sun. The black hole, if you're talking about the black hole. And R is the distance to the center of that object. The distance from the object that's trying to escape to the center of the object that it is trying to escape. Let's do some, obviously M has units of kilograms, and R has units of meters or kilometers or whatever you want. Great. Let's do an example. What is the escape velocity from the surface of the Earth? We've got a mass, 6 times 10 to the 24 kilograms. We've got a radius, 6.4 times 10 to the 6 meters. Let's calculate the escape velocity from the surface of the Earth. Okay, let's go back to our whiteboard. Let us erase all the stuff that was on there before, and let's try this equation out for size. Great. We know that the escape squared is sorry, 2gm over r. I momentarily forgot if there was a 2 there or not. I had to go look it up. So we know that G, 6.67 times 10 to the negative 11. Meters cubed per kilogram second squared. G, we know that M is 6 times 10 to the 27 kilograms. Sorry, 10 to the 24 kilograms. We know that R, now R is, in this case, is the radius of the object itself, right? And that only is because we are going from the surface of that object, right? If we were above the surface of the Earth, it would be not the radius of the Earth itself, it would be the distance from us to the center of the Earth. When you're standing on the surface of the Earth, though, the distance to the center is the radius of that object. In this case, 6.4 times 10 to the 6 meters, or 6,400 kilometers. Okay, now, we have this. We're not going to want this to be squared. Let's take the square root of both sides. VE squared square rooted is just escape velocity. Escape velocity is really square rooted 2gm over r. Okay, let's do this out. We have the 2. We have a 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. All divided by, oh, sorry, times the mass, which is 6 times 10 to the 24 kilograms. All divided by 6.4 times 10 to the 6 meters. That's a lot of 6s. Okay, let's do the numbers first, and then we'll do the units. I'm going to calculate, I'm going to plug this into a calculator in a minute, but let's do it, try to do it in our head first. And let's do the inside the square root, and then we'll square root the whole thing. So let's just do the numbers. We've got 10 to the negative 11 times 10 to the 24. You just add those exponents. So that's going to be a 10 to the 20, 10 to the 13 or so. Now you're dividing by a 10 to the 6. That's going to give you a 10 to the 7 or so. 10 to the 7, you probably have a 10 to the 8 because you're multiplying 2 6s and a 2 here together. So you're probably at 10 to the 8. You divide that, you take the square root of that, you cut that 8 in half to 4. We expect something like that for our velocity, which isn't actually what I get at all. So something went wrong there. Anyway, you do this all math out. Test me if I'm wrong. I will put an addendum if I do get this wrong. Plug these all in, and you get, without the square root, and then do the square root, I think you'll get a number that is, oh, that is right, 10 to the 4, 11,000 meters per second. I think there's an error in my notes here. 11,000 meters per second is our 10 to the 4, and I think that's right. This gives you 11 kilometers per second. 11 kilometers per second is the speed you need to be going to leave Earth's orbit and not come back. If you want to go to Mars, you need to build a rocket that can go 11 kilometers per second. Remember what the orbital velocity of the Earth was. It was just a little bit less than this. It was 8 kilometers per second. You have to get to 8 kilometers per second if you just want to orbit the Earth. Here's the Earth. You just want to go around it. You need to get 8 kilometers per second. If you want to leave it and not come back, you need to be going 11 kilometers per second. You need a bigger rocket to go to Mars than you did just to orbit the Earth, because you need to get significantly faster in speed. All right. I'm going to ask one thought question, and that is this. Let's go back to our PowerPoint slideshow. And that question is this: what happens to the escape velocity from the surface of an object if you shrink it, if you make it smaller? You can pause the video. You should answer it. You should write down an answer. Okay, let's talk about the answer now. If you shrink an object, what happens to the escape velocity? Let's go back and look at the equation. Let's go back and look at the equation. VE is the square root of 2gm over r. If you shrink an object, the surface of that object, you're getting closer to the center of it. And you're standing on the surface, you're getting small. R is getting smaller. What happens to the escape velocity if we shrink an object? R gets smaller, it's in the denominator, VE has to go up. So if R goes down, the escape velocity has to go up. Okay, we will come back in the next video and think about the implications for that for black holes. So come back.